Let's talk about it. Let's talk about it.
David said it was A. Then he said it was B.
Oh, you gonna blame me?
Yes.
It was B.
Think about it. Think about it. As the size of the atom gets larger, descending down the group, it requires less energy to take the valence electron away because they're farther away from the nucleus. Ionization energy decreases with increasing size. It's the opposite of the trend for size. So the answer here is second ionization energy. Group 2 elements actually get more reactive with water, more explosive. The solubility of hydroxide increases. That is just something you're supposed to straight up memorize. I put 1 mark of it on the quarterly. A lot of people got it right. And stability of carbonates actually increases. And what that means is that it takes more energy to decompose them. It takes more energy. It's another way of saying it takes more energy to decompose. And so the answer here was B, second ionization energy. All right, so with that being said, let me just double check that I am recording. We've got a hefty lesson today. Before we get into the lesson, I just want to go over a schedule. Let's go schedule and then learning objectives. Here is your schedule for the remainder of Unit 3. Today we're going to cover gases, RTP, STP, and ideal gas law. We have a bunch of math to do today. I'm also going to go over limiting reagents, which is a topic from pre-ACE chemistry that might have been forgotten. We'll touch base on it today. There's usually not a ton of questions about it from Cambridge. They show up every once in a while, but we'll go over it. Empirical formulas homework. You need to have the screenshot that you got 80% or better with the Science Geek. That's due online Monday night, 10:30. Pre-lab work. Some of you already started it. I saw you submitted. This is due by beginning of class. If it's online, the quizzes is due Monday night, but the other part is due beginning of class because next class we're going to do another titration. So we have on Halloween titration lab number 2. And so this time you will do a full titration with your rough titration and your accurate titration. You will be given a decent amount of time in class to do that, more than 45 minutes. And so you'll have your second titration with the second possible indicator you could have on that day. Just remember that day as well is our standard tutoring day. So I just wanted to remind you that tutoring times are normal for the next 3 weeks. Unit 3 homework, written homework 3, you're going to receive it today, but I'm not going to make it due until next Wednesday. That'll give you time if you need to work on it during tutoring to be able to do so. There's a lot of material in the 3rd written homework because it includes concentrations and it includes aqueous solutions, like all the stuff we did with ionic equations, and what we do today. So it's a hefty homework. All Cambridge questions, remember. Then we start redox next week, Thursday. We start redox next week, Thursday. And we have a couple of lessons. It's actually pretty much almost the same as pre-ACE chemistry, which you learned in redox. It's a revisitation of redox reactions, what they mean when you have redox, how to calculate oxidation numbers. And then there's a redox titration lab. So there's actually titrations can be done with acid-base reactions, or they can be done with redox reactions. And so we'll be doing a redox titration lab, which is technically our titration lab number 3, on Wednesday, November 8th. Then Monday, November 13th, we're going to review Unit 3, which is hefty, right? And then Tuesday, November 14th, there'll be a tutoring review as well. So you'll have the in class for 2 hours and then after school the next day for an hour. And then Wednesday, November 15th, we're going to go ahead and fit that Unit 3 exam before Thanksgiving or before fall break. That way, when we come back from fall break, we're going to start organic chemistry. So that gives us a natural line. Now, I know I'm going to see you on Friday, November 17th. We'll do something like that day because that is the day of Turkey Bowl. So, yeah, this class will be the last class before Turkey Bowl, most likely. If they do last year I know they did 1 hour each class period. So like 1 hour, second period, 1 hour, fourth period, 1 hour, sixth period. But Turkey Bowl is a very fun day. I'm not gonna do anything stressful that day. You'll deserve a break, especially after taking the exam, the class period before. The other thing I wanted to say for the quarterly exam, overall, I continue to be impressed by your group. You had the best average performance on a quarterly exam of any group I've ever tested in 10 years. So you earned your donuts. And so everyone who's taken it so far has passed, at least with an E or higher. And so, of course, it's the easiest quarterly because it's the least amount of information, but still, everyone is doing really well as a group. And so you should be proud of yourself, continue to put in the work, continue to put in the effort so that it pays off at the end of the year. But I'm just saying that I was actually really impressed when grading these. There was a lot of C levels. That was the predominant level that I saw, which, netted the 110 in the grade book. So if you got a 110, there was only one B level, one A level, and like a plethora. I can't say the amount because I don't remember, but there were a ton of C level scores.
But
So-
what did if you had a B, what did you get a B?
A B level is a 110 and a C level is a 110.
That's what I'm saying.
So anyway, great job. We must continue on the good. We're actually on good pace right now. The better pace we're at, the better off we'll be. Actually, for the end of the year, the more labs I can fit in. That's why every day you see we're working hard every single day so that we can build in those opportunities as we're going along. I also know we're losing that day for Turkey Bowl technically, so that's why you'll always see me on pace. I have a schedule I can see every year for the past 10 years I've been teaching exactly where we're at this year versus where I've been at other years. We're a little ahead. That is a good thing. Because remember, every day we fall behind is a day in April that I have to teach a lesson. And you don't want that. Because you don't want to go into April still having to be learning new content when you've got your exams in May. So that's why you see the hustle. The hustle is always on. So here we go. On the hustle, what do we got to do today? Math is the quick answer. I am so sorry, but a lot of this unit is math related. What we actually have to do, this is the last new day of moles calculations, and so we're specifically going to be focused on gases. Some of you may remember gases from last year. We did moles to grams with the molar mass. We did moles to moles with the balanced chemical equation. And we did moles to liters with 22.4. And I remember you asked me about that chart. I didn't have the time to look for it last night, but I will look for it and give it to you probably next week at tutoring for Damani. I know that you had mentioned the chart I gave last year. I'll look for it. I know it's in my previous materials. But we actually have done, in previous chemistry, we did some of gases before, but there's some alterations. So perform calculations including use of the mole concept involving volumes of gases, e.g. in the burning of hydrocarbons. What does that mean? Combustion? What's a hydrocarbon? Something like this, right? They're like, ooh, burn. What volume of gas will you get? And then we also need to look at least at the concept of limiting reagent today. Then we're going to look at what's called the general gas equation. When we are looking at temperatures other than standard temperature or room temperature, we have to use something called the general gas equation, which Leon Cambridge, I've never heard it called that. I will call it, you'll hear me call it, and most people, any reference you see that's an American reference is going to call it ideal gas law, actually. And it's PV equals nRT, including the determination of MR. What's MR? So molar mass. So when I read this, I read math. Do you read math too? Get ready. We're problem solving today. There'll be a couple opportunities that are your turn for solving questions, and I have some extra donuts. So I told you, pay attention today. You may get called on. for some donuts. All right, gas volumes. Here we go. First definition is molar volume. Molar volume. What this means, volume of a gas in 1 mole of a gas. The volume of a gas is dependent, because remember, we learned about gases a little bit. We learned the couple of ideas of the kinetic theory that showed up on the quarterly, didn't it? And you may or may not have remembered them. But with the volume of a gas, remember that they fill a lot of space. Gases fill a lot of space, but there's actually a certain amount of space they fill in a closed container. And that's given by what's here. And so this is a relationship, and a relationship I would encourage you to memorize. However, it is in some constants that Cambridge provides, which I'll show you shortly. You should recognize that 1 mole of a gas is 24 decimeters cubed at RTP. RTP stands for room temperature and pressure. RTP is slightly different, interestingly enough, than STP. And 1 mole of a gas fills 22.4 decimeters cubed of space at what we call STP. STP being standard temperature and pressure. Standard temperature and pressure is what's in like a standardized book that's 25 degrees Celsius. Like it's a straight up 25 degrees Celsius, 1 atmosphere. Whereas room temperature pressure is actual regular conditions. Like in an average room, what is the temperature? And so it's a little bit confusing, but what you're gonna need to remember is you're looking for RTP versus STP. So there's actually 2 different numbers. I bolded one of them. Why? Because this is the one that's used in about 90% of questions. In 90% of questions I've seen, that means there's a 1 in 10 off chance you get the other one. But in almost every question I've seen, and my fun time is pouring over Cambridge exam. I see that. So that's why I bolded it. Because out of the 2, if you have to memorize one, the one you're going to see more questions on is RTP in this class. And so this is 1 mole is 24 decimeters cubed. 1 mole equals 24 decimeters cubed. Is that something? Does that sound like a conversion factor to you? That's totally a conversion factor, which means it could be written as 1 mole over 24 decimeters cubed, or 24 decimeters cubed over 1 mole. You may want to write that down because that is one of the ways to solve questions quickly is by using conversion factors, because really it just sets it up to, do I divide by 24 or do I multiply by 24? That's what the conversion factor does for you. While I'm waiting, let me see if I can pull something up. I just want to show you something real quick. It's on my speed dial. The Cambridge website. Let's see if the internet's going to work. I want to show you something real quick. before we move forward. That's a little over here. Of course, as soon as I. Alright, so what I'm going to is the Cambridge support website. I want to show you something real quick. I'm pulling up random paper 2. What's paper 2? Written. Okay. So I'm going to go to the end of a standard paper 2. What's the last page? Look at the page right before it. Take a look at what's here. This is on every paper 1 and paper 2. So just so you're aware, and I will give this to you for the Unit 3 test. What's given to you is specifically Avogadro's number, the volume at STP, the volume at room conditions. You just have to read the question right to know which number you are working with. Are we okay with that? Yes. I pulled it up so that you can see what do you need to know. Anything that's not here. So basically, on a paper 1 and a paper 2, these are what they give you. They give you the stuff here and they give you a periodic table. Other than what's on those 2 pages, everything comes out of your brain. Got it? So I just wanted to be clear about that. All right. With that being said, now that you know that makes this hopefully a little bit easier. You just have to know which number to work with, right? So let's go. First question, checkup 19. Calculate the volume in dm cubed occupied by 26.4 grams of carbon dioxide at RTP. So, which number should we be working with? It says RTP, so that means we're going to work with 1 mole equals 24. I know that we got to work with this. Okay, but what do we have? Do we have moles?
No, we have grams.
So where should we start?
100 grams.
So step 1, I'm just going to write a 1 here. We're going to change grams to, this is just thinking process. So in order to change grams to moles, we decided we're going to use a formula for that. Do you remember what it was? Moles equals grams over. So if you're going to use this formula, you got to memorize it, which means you got to write it over and over again until it sticks. So to solve for grams, that we need to multiply by? Or I have grams, so it's actually just divide by the molar mass, right? I have grams. I want moles. So how many grams do I have?
26.4.
So it's 26.4 on the top, and the molar mass of carbon dioxide is
44.
beautiful. How do we get that? We know carbon dioxide is CO2, carbon is 12, oxygen is 16 times 2 of them. So Cambridge expects you to be able to do this real quick. 12 plus 32 is 44. They expect that we went through all the work of explaining ourselves in previous. 26.4 divided by 44 is
0.6.
0.6 what? Moles. Now decision time. Yes. Is that sharing anymore? It says sharing. It's lying to me. How dare it? All right, I'll get back on and share it again. Thank you, Sophia. So I told you, you gotta watch it to make sure it's doing what it's supposed to be doing. Last year, I don't know if you all noticed, last year and the year before, I would teach over there I'd be watching two screens at the same time as I was teaching to make sure I was showing the right thing. I no longer have to do that. 0.6 moles. Now what?
0.6 times 0.6 divided by 24 or 24 divided by
What's the decision? Do I multiply by 24 or divide by 24, right? That's the decision because step 2 is to change moles to decimeters cubed. Recognizing that you have to cancel moles, that means you have to divide by moles and you have to multiply by the volume. So multiply by 24 is absolutely correct. It would be 0.600 moles. And then if I show my work properly, it would be 1 mole at the bottom and 24 decimeters cubed at the top. Cambridge does not give marks on showing dimensional analysis. To be clear, as long as you just write 0.6 times 24, they would give you the mark. Okay. So 0.6 times 24, what do we get from that?
14.4.
14.4. All right. That was our first baby step, as simple as it could be, question. Let's take a look at the next one. So, what makes this next one just a little bit more difficult? What's up with this next one? On the bottom. So it gives you the volume. It's asking for mass, so it's opposite process, right? But what else is going on here? Centimeters cubed, but the conversion is with decimeters cubed. Do we know how to solve that real quick? Divide by 1,000 or move the decimal over, which is my preferred method, but you can use either. 0.120 decimeters cubed. I usually just literally do that. I cross it out and write it in decimeters cubed. So now what do? I've got the decimeters cubed. I need to change this to? Right. It's going to be volume to moles and moles to grams. So volume to moles. What do? Divide by what number? 24. That is correct. So that gives us the answer in moles. I did that and I got, pretty sure, I just did dimensional analysis. But if you break it up step by step, it would be 0.005. All right, now what do? How do I go from moles to grams?
Multiply by the relative locality time.
Multiply by? Perfect. So we know, I'm just showing the proper steps, but as long as you know you multiply by 4, you would get your answer, which is 0.02 grams per kilo.
Let me go from 120.
So there's 1,000 centimeters cubed and a decimeter cubed is one way to look at it. I usually just use this method. King Henry died unusually drinking chocolate milk, and know that if I move over one spot, I'm actually moving over when it's cubed 3 spots. So instead of moving over by a power of 10, I'm moving over by a power of 1,000. So that's why I get the answer right. But you can always take 120 divide by 1,000. You get decimeters cubed that way. I'll bring this up later on as well, but that's the idea. All right, how do we feel about this so far? This is called, so what's this topic again? It's called molar volume. The amount of volume a gas occupies when you have a mole of particles of that gas.
Oh, it's because it's cubed that you have to divide by 1.
That's right. Instead of 10.
That's why I was.
You ready to see paper 1? So how is this approached in paper 1? This is what it looks like in paper 1. What mass of gas would occupy a volume of 3 decimeters cubed at 25 degrees Celsius and 1 atmosphere? They didn't tell tell you whether this was room conditions or whether this was standard. So they just told you here, hey, this is the number you should use. Y'all, use that one. So, what should we do? Where shall we head with this? We want to know which of these gases occupies a specific volume of 3 decimeters cubed. Would it be 3.2 grams of oxygen, 5.6 grams of nitrogen, 8 grams of SO2, or 11 grams of CO2?
How many?
1. What? Why don't you find the moles of each one? Could you find the moles of each gas? So find the moles. Do 3.2 divided by for oxygen would be 32. So that would be 0.1, right? 5.6 would be divided by 28. That's 0.2. 8 divided by the molar mass of SO2 is 64. I'm doing it quickly. Would be 0.125. And 11 divided by 44, I think is 0.25 off the top of my head. I found the moles of each gas. Why would I want to do that?
So then you just have to convert volume to moles.
Because then all I got to do is take 3 and divide by 24. And then find out which amount's the same. The answer is C, David. You got the mark. It's multiple choice. so it's C. I actually did that pretty quickly, didn't I? Because I knew exactly what I was looking for, though. So this could be a question that takes 3, 4, 5 minutes on a paper 1. Do you have time to spare? Not really. So you go for it if you feel confident in a method. If you look at it and you're like, I don't know what I'm looking at, you skip it, come back at the end, and make sure at the end you bubble in an answer. If you ran out of time, you just bubble in an answer. Don't leave anything blank on a paper 1, because you could get a mark. Like, even if you don't know the question, you get a 1 in 4 chance of getting it right. All right, so that's the part 1 of gases. Now I'm going to bring up something from freeze chemistry that you're not going to see much of in this class, because it's barely ever tested. But it could be. So I have to at least mention it. And I spend a full lesson going over it in year 1 chemistry. It's called the limiting reagent. And so the concept of the limiting reagent is, what if you're not told what reactant runs out in a chemical reaction? Meaning, when we look at stoichiometry, almost every question that we have, they tell you that we have this reactant, how much product do we make? Grams of this to grams of that, moles of this to moles of that. But that's assuming that your other reactant, if there's another one, is in excess, that you have plenty of it, and that you've already been told what's limited. This is the scenario that you're not told which reactant you run out of first. So let's take a look at it. 3.7 gram sample of copper 2 carbonate is added to 25 centimeters cubed of a 2 molarity hydrochloric acid. And you are asked, which volume of gas is produced under room conditions? First of all, look at the question. Where do you think you're going to need to start with this? You're given an amount of grams of copper carbonate. You're given an amount of volume and molarity of hydrochloric acid. And they're asking you how much volume of gas is produced. Anybody have a suggestion of where we could start?
The water.
Do we even know what's made here?
Nope.
Did we figure that out?
Yes.
Step 1. We need a balance equation. They didn't give you one. Hashtag rude. So what's our balanced equation here? We've got copper 2 carbonate. What's the formula for that? Copper has a +2 charge. They expect you to know that carbonate is
CO3.
CO3 with a -2 charge. So copper carbonate is CuCO3. That's going to be a solid. It's an ionic compound. Ionic compounds are solids. Unless they're in water, and it didn't tell you it was in water. We're going to throw that copper carbonate into some hydrochloric acid. So what's the formula for hydrochloric acid?
HCl.
All right, beautiful, beautiful. Which is in what state of matter? Acid is only acid when it's in water, which is aqueous. They've given you this. You can't figure out how much gas is produced if you don't know what's produced. What type of reaction is this?
Double replacement.
Double replacement. So they expect you to not only know what type of reaction this is, but know what the products are. So what are the products of this reaction? Supposed to Chris, right? Chris, like, put the outer two parts together, put the inner two parts together, you get CuCl2, which is aqueous, a compound in water,
Plus.
and H with CO3. H plus 1 with CO3 minus 2, what does that make you?
H2CO3.
And does anybody remember what I said about H2CO3 that you are supposed to memorize? It breaks down,
Oh, it breaks down to
Into
H2
water?
and carbon dioxide.
which is why you saw me writing up here. It breaks into water and,
Carbon dioxide.
which is a
Gas.
gas. Is it balanced? Okay, but only to balance it, all you gotta put the 2 in front of the HCl. So that's the good news there.
Yeah.
Are we even remotely close to done with this question?
No.
That was step 1. Step 1 is to make the proper balanced equation. So what do we do now?
Take the moles.
Right. So we're going to have to figure out from each reactant how many decimeters cubed of gases made, right? So you've got 3.7 grams of CuCO3 as your one reactant. That's reactant 1. And what's reactant 2?
2 moles. Yeah, 2 moles of
It's 2 molarity.
of hydrochloric acid.
25 centimeters cubed, right? HCl. So where should we go from here? I've got the grams of CuCO3. What is the question asking me to figure out?
Volume.
Volume of,
Gas.
which is volume
Carbon
of
dioxide.
CO2. So anybody now have a suggestion of what to do? You've got the grams of CuCO3.
Convert it to moles.
Can't you convert that to moles? Sure, let's do it. So that's where I went next. I said, okay, I have 123.5 grams of CuCO3, that's the MR. And that would be in how many moles? 1 mole. CuCO3. But what do I want to get to? I don't want to be in CuCO3, I want to be in carbon dioxide. So what should I do next? Well, you could just divide these two numbers. What do you get? Do 3.7 divided by 123.5. I get 0.03. Round it.
0.0.
Moles. Where next? That's CuCO3. What do we want?
CO2.
So once we have moles, we can say 1 mole of CuCO3 will give us 1 mole of carbon dioxide. What does that mean?
Oh, that is going to be equal.
That it's going to be the same. So we now know that we have 0.03 moles of
Carbon dioxide.
CO2. The question's not asking for moles, it's asking for.
Water.
So now multiply that by
24.
4, right? And what does that give us? 0.72. Are we done? Is that the answer?
Yes.
Are you sure? In a limiting reagent question, you were given amounts for both reactants. You weren't told which one you ran out of first. You haven't done anything with hydrochloric acid yet.
So you
You
have
have
to
to do the same thing. So now start with your information for hydrochloric acid. You've got concentration and you've got volume, which means you have to use that's why I did two per page. Concentration equals moles over decimeters cubed, right? So you would do 2.0 is the concentration. We're looking for the moles, and the dm cubed here is 0.025. Multiply both sides by 0.025. What does that give us for moles of HCl? 2.0 times 0.025. I did 0.05. But now what? No. We're not looking for HCl. We're looking for CO2. So what's the relationship between HCl and CO2? 2 HCl is for 1 CO2. So you've got to divide this by 2.
like 0.0.
Right? That's moles of CO2, and now you have to multiply that by 24, right? And that gives you what number?
0.6.
Because it's told to you here. Well,
It's not told in this one.
it's not?
No.
Yes, it is. Room conditions.
Oh.
So you could look at the thing in the back and say it's 24 because it's room conditions, not standard. 0.60. And which of these two amounts is less?
0.6.
Which means that the answer is A. This is limiting reagents. So limiting reagents basically is that you're given multiple reactants, amounts of multiple reactants, and you have to figure out how much product is made from that. This is a paper 1 question. It is worth 1 mark. All that. This is what I would call level 3. Would you agree, based on what you've seen here?
Yeah.
2.5? I'd say level 3. So why do I assess it that way? Well, first you've got to make your formulas correct, every single one of them. Then you've got to balance the equation correct and know that this is a weird double replacement that has a part that breaks apart, right? Then you've got to run through the reaction for both reactants to do the full stoichiometry from the reactant to the product. You've got to know the states of matter for all your products and then compare at the end to look for the smaller amount produced, because the smaller amount produced will be from the limiting reagent. So you're welcome. I'm not really giving you a lot of homework on this. So I'm giving you a you're welcome in advance, and the only reason I'm not is because Cambridge does not heavily test this. It shows up on a random every once in a while question. You make the choice if you want to do it for the 1 mark or not. It's up to you. It's not impossible to solve, it's just the tediousness of it is, I would say this would take like 10 minutes to do. Yes, yeah. I call these questions Cambridge time wasters. You put them on the test to mess you.
It's just 1 mark. What's the difference?
But not everybody thinks of it that way. So that's why you've got to think of it the right way. That mark is worth the same as the one that says decreasing ionization energy down to the groups.
I'll leave that
If
for last.
anything, I would do it.
Never have.
I would do it, man.
You would do it?
I would do it.
I would do it at the end.
Yeah, I'll do it at the end.
You're gonna have to make choices at the end of the day. You want to get the college credit, get the ACE science credit. So my suggestion is not to do it in the beginning. Wait for the end if you are going to do it, okay? And if you aren't going to do it, just pick your best guess. All right. So next thing, and And this is going to lead us to technically our final topic, but it is a pretty big topic. We've looked at molar volume of gases. Molar volume basically is a constant. It tells us that at a certain temperature and pressure, a certain amount of volume will be occupied by 1 mole of gas. But what would happen if we had different temperatures? If we altered the temperature conditions, or if we altered the pressure conditions? Well, changing the pressure and changing the temperature will alter the amount of space that's occupied. So the first relationship you need to be aware of is as the temperature increases of a gas, this will cause the pressure to also increase. Does that make sense with kinetic molecular theory? Pressure means gas hitting walls of container. So if I have a closed container and I increase the pressure, it means the gas is hitting the walls
At a higher
at higher pressure. So high temperature, high pressure. Raise the temperature, pressure raises. We call this a direct relationship, meaning whatever happens to one thing happens to the
other.
other. In mathematics, we a lot of times look at direct relationships and inverse relationships. And these relationships are what's going to give us the general gas equation you're going to see as the other standard. All right, so here we go. The volume, or if I decrease the volume of a container, what will happen to the pressure? Let's think about it. Let's say that I have a container and I have try to keep it easy. 6 gas molecules. These arrows are the gas molecules going like this, right? What happens if I half the volume, but I still have the same amount of gas molecules at the same temperature?
The pressure will increase
Do I hit the container more often, the edge of the container, or less often?
more often.
Hit it more often, right? So decreasing the volume increases the
Pressure.
pressure. And another way of saying that, decreasing the volume increases the pressure. Because pressure is decreasing the volume, increases the pressure. Because for the same amount of particles, they're going to hit the end of the container, more often. If it hits the edge of the container more often, that means more pressure is generated, if that makes sense. More force is generated because it keeps hitting it. So as you constrict it, that's why I'm trying to visualize it for you. That's what's going on. And so
So the more volume, the less pressure.
the more volume, the less pressure, because that means that if I had a bigger volume, right, and I got my same 6 molecules, they have to travel farther to hit the wall of the container. Does that make sense? So that means that this is what we call an inverse relationship. Meaning when one goes up, the other one goes down. So engineers and physical scientists manipulate conditions to, like, they'll manipulate the pressure or they'll manipulate the volume to push a reaction to go a certain way. Or they'll change the temperature to do the same thing. So this is what we call modifying conditions. We can modify conditions to force reactions to go a certain way. Raising the temperature, of course, causes particles to hit each other more often. And you can also change the volume of the container or the pressure in the container in order to do this. So it's just some things to point out. This actually ties directly into ideas of engineering later on, and ideas of how you can modify reactions later on in the class. Right now, we're just going over these key relationships. And so the last law is called Avogadro's law. If we increase the amount of particles in a container, so if you think about this, if you've got the same volume and the same temperature, I'm going to do my best. I'm a terrible artist, and you know that. And I apologize in advance. That's as close as I can get with the same size. Imagine these 2 boxes are the same size, okay? And it occupies the same volume. If I have 2 molecules of gas here, and I have 4 molecules of gas here, which one generates more pressure? 2 molecules of gas or 4 molecules of gas?
Four molecules of gas.
So 2 molecules is lower pressure, right? 4 molecules is higher pressure because the particles are hitting the wall more often. We okay with that idea? So if I keep the volume the same, I keep all the other conditions the same. Volume stays the same, temperature stays the same. I'm not modifying those conditions. I just change my amount. I add more. I will increase the pressure as a result. And so these are key relationships that are important to recognize. All of these relationships, along with a constant, lead us to what's called the general gas equation, which means if we modify the pressure, the volume, the temperature, we can change any of these conditions. We have the amount of moles. So this goes back, this equation that we're about to go to, first of all, only works for ideal gases. If you don't remember what that means, gases that are ideal are exactly as they should be. Low molar masses, low forces of attraction, great gas. No hydrogen bonding, great gas. So, volume which a gas occupies depends on 2 things. Its pressure. There's a new unit you need to be aware of. I've never discussed this before. It's called Pascal. This is the unit of pressure for force hitting a container. It is the same dude. It's the same dude who did Pascal's triangle. Well, we're gonna lovingly call it Pop. And later in this class, you're gonna see Papa. I'm just saying. When you have 2 Pascals multiplied by each other, it's Papa. We'll learn it later. And then temperature. The unit of temperature that you must use for this formula, and for much of this class, is called Kelvin. Has anybody ever heard of Kelvin before? The Kelvin scale?
See that?
So absolute zero is based off the Kelvin scale. Fun fact. Absolute zero is where all particle movement stops. Based off of what's called the Kelvin scale. It's the temperature at which all life stops. Nothing moves anymore. What you need to know, you're going to have to memorize the conversion between Celsius and Kelvin. It is, so memorize. Put this on your memorize list. It's an easy conversion, meaning to go from Celsius to Kelvin, you add 273. 0 Kelvin is where all movement stops, meaning molecules don't even vibrate anymore. There can be nothing in the gas phase at 0 Kelvin, not even helium. Everything is a solid, like a frozen planet. Question. We use an American scale here of temperature. Do you remember what it is? Fahrenheit. What do you think the Fahrenheit temperature of 0 Kelvin is?
Negative something. Negative 272.
It's in the, well, it would be negative 273 Celsius, right? So if Kelvin is 0, right, C plus 273 equals 0, then absolute 0, where everything stops, is negative 273 Celsius. But does that mean anything to you? Do you know what negative 273 Celsius is? So how do you go from Celsius to Fahrenheit? Cambridge doesn't need you to memorize Celsius to Fahrenheit, but it is a conversion you may know or not know. Fahrenheit is 1.8 times Celsius plus 32. So just go ahead and do 1.8 times negative 273 in your calculator plus 32. And that'll give you an idea of how cold it has to be for life to stop. For all life to stop. It's negative 459.4 degrees Fahrenheit. Is there any place on Earth that naturally reaches that temperature? No. There's not. There's There's no place on Earth. Are scientists able to do it in a lab? Yeah, they have these big machines and they do it. But it's just an aside for you to recognize how cold it has to be to reach 0 Kelvin. So nothing reaches 0 Kelvin. That's the idea. Kelvin cannot be 0 in any of our equations. It cannot be. You can't have a gas at 0 Kelvin. It doesn't exist. This is beautiful for a reason that you will see later. And also, this delves into physics ideas. Remember, chemistry sometimes goes into physics ideas and goes into biology. This is a physics idea. So if you love this type of content, take a physics class. All right, checkup 3. This is what the textbook for Cambridge Chemistry wants you to do. Convert the following temperatures from Celsius to Kelvin. Formula is C plus 273 equals K. Can we do this?
580.
Yes. So the first one, 245 plus 273 equals K. So literally, if you're given Celsius, what you got to do? Add 273 to it. And this is going to get us to 518. Are there any Cambridge questions that they would ask you just to do that? It's going to be one step in a large process. Just be real with yourself here. All right, next one, negative 45 degrees. Negative 45 plus 273 is 228K. And so Kelvin, the reason Kelvin is used and developed is because in order to use the gas law, you have to have things that can be gases, and nothing can be gases in the Kelvin scale of 0. You'll never encounter the number 0 for Kelvin. So if you ever get an answer, by the way, you're doing the math, you're looking for temperature in Kelvin, and you come up with negative for a Kelvin answer. What do you know now that I've explained this?
You managed to create something impossible.
Which means that it's probably wrong. Recheck your word, please. Just assume you're wrong. You may get some error carried forward if you showed your work. But there was definitely a mistake made somewhere. All right, so this all leads us, all of these relationships that I have told you, leads us to what's called the general gas equation, the ideal gas law. And so this is also called the general gas equation, and this actually has to be memorized. Sorry. Yes. Yeah. So not only does this have to be memorized to solve questions at different temperatures, pressures than standard temperature and pressure, you have to memorize the proper units on top of it. Meaning, in this equation, for it to work, your pressure has to be in pascals. The way that the equations develop, the unit of pressure that you must insert into the equation for P is pascals. Could Cambridge give you another unit, like kilopascals, and then you have to change it? Volume must be in meters cubed. So if you've got decimeters cubed or centimeters cubed, you're going to have to change it. Moles is moles. And N stands for moles. We've seen N stand for moles before. N stands for moles. So the N in the ideal gas law is moles. R is a constant. Quick question. Does this have to be memorized? Let's check it. I did believe I showed you something here. If you know where to look for it, I will be giving you this on the next step. Is it there?
Yes.
And it says hard. Your questions, because you do a lot of practice problems, you're probably going to memorize it, but just in case you need it at the end of the year on the Cambridge exam and on the Unit 3 test, I'm going to give you this paper, okay? Yes?
Yes.
It's your little helpful, this is what you get. Remember I go by WWCZ? What would Cambridge do? If Cambridge gives it to you on a test, so will I. If they don't give it to you on a test, then I won't either. All right, here we go. Temperature, I have explained why, but I'm just gonna bring it up again. Temperature in Kelvin has to be in Kelvin. Because Kelvin can never be 0 for a gas. Mathematically, all of you in 8th math.
Poor Justin.
I just want to bring something up. I'm dividing both sides here by RT just to show you something. If Kelvin could be 0, you would end up with a 0 on a denominator. Can you ever divide by 0? Or you get something called undefined. We only work with things that exist in this class. So this formula was created so that there's no possibility for you to divide by 0. Does that somewhat make sense?
Yeah.
So that's why it's based with Kelvin. So if you see Celsius, the quick story is change it to Kelvin. Because if they give you 0 degrees Celsius, you won't be plugging 0 into a formula and you're going to be coming up with undefined. Good luck. So make sure you know your units. Beforehand, let's just remind ourselves of some quick conversions. In other years, I actually taught this first before I taught conversion, so that's why you see some questions here. But let's go review. How would I change centimeters cubed to meters cubed?
You would multiply by 4. That was a really bad guess on this.
Like 2 plus 3. I have a good visual memory. So, how would I change centimeters cubed to meters cubed? What's our suggestion?
Move the decimal over to the right.
Remember that this is where meters, liters, and grams are.
Oh, okay. So then move it to the left 6 times.
So we're going to move it here to the base unit. Because 1 letter means base unit. Move your decimal over how many times?
6.
Or divide by 1,000,000, your choice. Divide by 1,000 and divide by 1,000 again. My preference is to move the decimal over 6 times. But that means you've got to know that you've got 4 zeros. Are you okay with this? Second one, decimeters cubed to meters cubed. How do we do that conversion?
Move to the left 3 times.
And so it's actually real simple then. It's just
0.2.
0.2 smart. Good? This is getting more familiar with how to do this? Because we did this in the first lesson of the unit, I believe. Feeling better about it? King Henry died unusually drinking chocolate milk. Yeah. King Henry died unusually drinking chocolate milk. All right, so practice problems time. And I told you to have an opportunity for donuts, I think. So there is a question that says your turn. I think I might be able to give you 2 opportunities, but let me go through a couple questions first so you get the idea. You're always going to be given in the general gas equation 4 out of 5 things. And you're going to be solving for the last of the 5 things. One of these 5 you always have. Which one?
R.
You always have R. It is always 8.31. You will never be solving for R. Which means the question's either going to ask you to solve for pressure, for volume, for moles. Wait, if they ask for moles, could they also ask for grams? Oh. Could they also ask for molecules? It's feasible, right? Feasible means like it could happen. Anytime moles is in the conversation, everything that's connected to moles is also in the conversation, depending on the level of the question, right? How difficult it is. I'm just being honest with you. And then you could be asked for temperature. And if you get a negative temperature as an answer, good luck. Yes.
The pressure.
All right, question 1. I'm going to go show you how to solve. Let's get started. My first question is gonna be, so we've got 0.25 moles of carbon monoxide. So I'm gonna underline that number, that's a number. What else do I have?
120 kPa.
All right, I've got that number.
10 decimeters cubed.
And 10 decimeters cubed. I've got three numbers. That didn't say we get 4 out of 5.
Yeah, the
Four.
first one is 8.1.
8.31. So I know my formula is this. Before you start plugging in numbers, what should you do?
Convert. Make sure it's in this.
You should make sure all your units are correct. If any of your units are wrong and you plug them in the formula, just assume your answer is also wrong. So let's check all of our units. What does pressure have to be in? Look at the formula, because you will have to memorize it, but for now, that's mathematician scientist. It's Pascal. The unit's named after him. All right. So, do I have Pascals here? But that's not Pascals. That's kilopascals. Are grams and kilograms the same thing?
No.
Neither are Pascals and kilopascals. So, what do we gotta do? Yeah, it's died. I'm usually drinking chocolate milk. And we
Antioxidants in the science acronym.
I didn't make it up. So, what do we do? Change kilopascals to pascals.
You're good.
Move it to the unit, right?
Yeah.
So move to the right 3 times. So this is 120,000 pascals. All right. Right? What's the only significant? Okay, next. Volume. Do I have a volume?
Yes.
Is it in the right unit for this formula? Unfortunately not. We're supposed to get meters cubed, and this is in decimeters cubed, so I have to. It's deci to unit, so that would be a movement of 1, but it's cubed, so it's actually a movement of 3. Dude, I hope you're starting to see how powerful the tool this is instead of just like multiplying and dividing by 1,000 all the time. Just move your decimals over. 0.010 meters cubed, now in the correct unit. All right, N, what's N?
0.25.
Moles. Is it supposed to be moles?
Yeah.
Is that supposed to be moles? Yes. R is always 8.31. T is I don't know. Right? So once you've got all the correct units, it's plug them into the formula, all the numbers, and do your math right. Plug your numbers into the calculator correctly. So I get 120,000 times 0.01 equals 0.25 times 8.31 times T. On the left-hand side, I got 1,200 when I multiplied these two numbers. And on the right-hand side,
I got 2.1.
I didn't round so much. I got 2.0785, but I don't think it will affect your final answer.
I got
so much.
2.0775.
Yeah, I got 775.
Then I just and that's next to T, right? So now what do we do?
Divide by 2.0775. You get your D, which is an answer that I will solve shortly.
577.
It literally did not change the final answer. 578 equals Kelvin. For temperature, you can round to the nearest whole number. 3 significant figures is fine. 578. Is that a feasible answer?
Yes.
Yeah. What do I mean by feasible? Does that exist?
It's not 0.
Oh, that's the equation.
Maybe it's Kelvin.
It's not 0 or negative, so a gas could have that temperature. Alright. How do we feel about this process?
It would be
Every day.
keep it respected. Absolutely wrong.
Alright. That's, yeah. Or like on those planets like Pluto, like the exoplanet, right? Yeah. Go ahead with process back.
It sounds like.
So- What do I divide by what? Temperature, I'm solving for temperature. It's a multiplication, so I gotta divide. Yeah, that's all multiplied by T. Alright, I'm moving forward in 5, 4, 3, 2, 1. We got one more thing to bring up. So, I hinted at this. Anytime moles enters the conversation, you could actually be asked for grams. And this is commonly asked for by Cambridge. So look back at our objectives, way back at the beginning of the lesson. It says state and use. What does state mean? You could literally be asked on a paper too, what is the general gas equation? And if you write PV equals nRT, you get a mark. That's what state means. State is an easy question, meaning that it's literally write down the formula. Those questions don't show up very often, but it's not impossible. If it's in the standard, it can be asked. It could be asked on paper too. It's an easy mark. Now, use means that's what we've been doing. Like plug the numbers in and solve it. In calculations, including the determination of what's this? Molar mass or relative molecular mass. So they could give you feasibly a bunch of information and ask you for the molar mass of the gas. They could then, with other pieces of information, ask you exactly what the gas is. So, like with the molar mass and some other piece of information, you can interpret what it is. So this is where we need to go. I need your full attention for this. If you like math, I'm going to give you a suggestion. If you like math, and if you don't like math, I'm going to give you another suggestion. If you like math, you should remember that moles equals grams over ring a bell? So if you like math, you should write what I'm writing. In order to solve for MR, remember that moles is the same thing as N. So where you see moles in the general gas equation, you can replace it with G divided by MR. Are you following me so far? You can rearrange this to solve for molar mass. How would we do that?
Divide by R, then multiply by
I suggest a different path.
You would,
If I want to solve for MR, yes. Somebody else asked first.
multiply by MR.
Sophia, go.
Multiply by MR on both sides and then divide by 20.
So let's do that. Multiply by MR, because we got to get it out of the denominator to solve for it. No, it's a multiplication.
divide.
So we would now have MR PV equals GRT. Believe it or not, once you do this, if you've got grams in the question, you could like just manipulate this however you want to solve for whatever you need. The most commonly asked question though is to solve for MR. It literally says it in the standard, right? So how would I solve this for MR? What would I do next? What's the proper
divide by
amount?
PV,
So let's do that in color.
divide by PV.
And we would come up with,
MR equals GRT over PV.
so if you like math, at least algebra, as long as you know PV equals nRT, and you know the formula to change moles to grams, moles equals grams over molar mass, you can plug in that information to figure out the relative molecular mass, and it gives you this formula. Now, if you have the grams, the constant, the temperature, the pressure, and the volume, you will directly be able to find the molar mass. If you hate math, it's not though. It's algebra. It's the letters. Algebra is a bunch of letters. If you hate math, you're like, no, not for me. Well, you could just memorize this. That's the other option. Memorize the second formula to solve for molar mass. For some of you, you prefer to do that. I actually prefer method 1 because I personally like math. But I just am giving you both so that you can decide what you want to do. Regardless, if you want to solve for molar mass, you're going to need the grams, the temperature, the pressure, and the volume. So let's do a question together, and then you'll have a question to do. Here's our question together. We've got 0.08 grams of liquid X. Is there an X on the periodic table?
No.
So what do we mean by liquid X?
Like unknown.
That's some kind of unknown. It sounds like some concoction. Liquid X. It was vaporized on top of it into a gas at 100 degrees Celsius. 23 centimeters cubed of vapor was formed. The atmospheric pressure was 1.02 times 10 to the 5th. Calculate the relative molecular mass. So first thing, do you know what we're being asked for here? What are we being asked for? That's a good place to start, right? What's the question asking for? So we're looking for MR, or molar mass, right? So we know a formula for that. You're either going to have to memorize it or you can find it. What's the formula? GRT over EV. That's a formula. But before I could start plugging numbers in the formula, if you learn something from what I did in the first question, what's step 1? Can I just like start throwing numbers in and be like, it's gonna work? Step 1, unit. You have to have the correct units. If you don't have the correct units, you're gonna mess up 100%. So, G, is that the right unit? Do I have the right unit for G? Yes. R, that is a constant. I always have it. What is it? How nice of them. Sometimes. All right, temperature. All right, what do I see for temperature? 100 degrees Celsius. Is that the correct unit? Do that 100 plus 273. So the right temperature is actually 373 Kelvin. What else? I got the temperature. What do I still need? Pressure. Pressure is 1.02 times 10 to the pascals. Is that the correct unit? Bless you. Unit check, correct. All right, last one. B. What's my volume here? What's my volume? 23 centimeters cubed. Because it's the thing that's cubed. Remember, volume is length times width times height. So it's whatever's cubed. 23 centimeters cubed. Is that correct? What I gotta change it to meters cubed. How many movements do I gotta make? 6? Yeah. Because remember, every time I'm gonna rewrite it. King Henry died unusually drinking chocolate milk. You're moving to the base unit when you move to meters. The little m next to C is milli, not the base unit. So you have to move over 2, but a movement of 2 is actually a movement of 6 because it's cubed. So this becomes point and 4 zeros, 2, 3. After my units have been converted, I now go where? Did you get the volume? 23, move over 6 times. Now what do? Plug in the formula. MR equals, plug in your numbers, 0.08 times 8.31 times 373 for the top, and the bottom is 1.02 times 10 to the 5th multiplied by 0.000023. I have a suggestion. There's a lot going on here. I would suggest multiplying all the numbers in the top first, multiply all the numbers in the bottom, and then divide. The reason why I suggest this, if you try to divide both of these numbers at once, if you don't do your parentheses right, it's going to multiply instead of divide. So my suggestion is for your calculator's order of operations to do the top first and then do the bottom. That's what I did. I got for the top 247.97. Check to see if you get the same thing. I did this earlier. And I got for the bottom 2.346. Then I divide those two numbers, right? And I got 106. Check to see if you got the same thing. Rounded. Check to see if you get the same thing from the math. Check your math. And make sure you're following along because, like I said, there were a couple marks lost on the quarterly exam where all the work was shown properly, but the math was put in the calculator wrong, and the question was only worth 1 mark. So 1 mistake means that you can't even get that 1 mark because there's no such thing as a half mark for Cambridge. So make sure you're plugging everything in the calculator correctly. Did you get 106? Anybody confused? Are we okay with this? This is your time to ask if you did get confused somewhere. I multiplied all the numbers at the top. I multiplied all the numbers at the bottom. And then I divided those two answers. Well, while I'm waiting, the next question is your turn. Whoever needs to go to the bathroom next. Alex? So I'm going to give you 5 minutes. See if you can solve this question. If you get it right, you may potentially get donuts because I'm going to pull up the spinner wheel.
No, I never get called on spinner wheel.
You never know. It could be your time. Wait, do you get free donuts? That means you didn't get called? What?
No.
Well, there are 18 students in the class, so that could be. It could be. But I think Julio got called like I don't know.
And the second
I
time
got
was
called
today.
You got called 3 times.
Messed it up.
Are you the record holder?
Yeah, I had the right
Well, I
answer.
don't know.
All the
I
other
called another time, but we let it slide because I wasn't there.
I see.
You see, if you would have asked me a couple days ago at this moment, we would have gotten another today.
If you would have looked at my
Today was not the day.
paper and listened to the other people.
Apparently today was not the day.
Need a break for that.
Pulling out the wheel, and I'm pulling down a countdown. No. You've got time.
8.350
You've got a full 3 more minutes.
equals 218. Oh, that's right. And then the second three. E times V, right? Each pressure, right? And since it's kilopascals, you have to multiply it. Keep the moles of rainbow every time. So it's
You can ask me to check your work when you have the answer.
I don't know if this is right. I should put it really big.
There you go. I got
It is not the correct
I
answer.
got it.
Check your unit.
See, I knew it. Miss, can you check mine? You round to like double number or?
To the nearest 0.1 because of molar mass and like that.
Okay.
Periodic table.
There you go, I got it.
That is correct.
That was smart. I'm just.
Positive words of affirmation. I was saying during the bell work, whenever you get something right, you gotta be like, yes, I'm brilliant, I'm amazing. And then if you get it wrong, I'm getting better every day. This is wrong, right? So think about what molar masses are, and one is a movement of one. But if you have something huge, you have to move up down. Kilo
Well, actually,
to unit,
that's why I got it wrong. That's right.
because it's kilo to unit. That's three spots away.
I really hope I get called up.
You have it.
There's no way I'm getting called up.
You have it. All right, we got 35 seconds.
You get it?
Miss, can you check mine?
If the first person doesn't get it, I'm gonna call someone else.
I volunteer to go.
It's rounded off, but it's fine. Let me check yours.
I volunteer. Is that enough? Can I volunteer?
That is not right. Alrighty, 5, 4, 3, 2, 1. Work has to be shown, remember. Like you have to have like work. That shows work.
Okay.
You got the right units there, stuff like that. Calling a name. Whose turn is it?
Come on. Oh,
Hakeem. Do you have it? You're still working on it? You didn't have it
listen.
yet?
Like I'm surprised because since my name is the first one, it has to be like three complete. Sure.
To get there? Alright. Calling again. Calling again.
Here comes my name.
I'm so good at this. It's actually me.
Oh my god! Take a donut. I still got 4 donuts again, so.
Oh, so that's zero. That was a zero.
I think I got a little bit more time. 86 points. Yes! Good! Take a donut. Alright, he had it, so here's the donut. Alex, oh, bathroom! You gotta tell him we got mixed out. Okay. Ernesto, you have it. I think I told you you missed it. Oh, he just missed it. Alright, I still got. Let me check your treasure. We'll have one for you. I'll finish one.
Good afternoon, Golden Line.
I still got 2 to give away.
Please remember to check your campus email daily and report to school in proper CA uniform.
Is that Jamie?
Also, wear a security badge around your neck at all times. Attention to the
Jamie! Alright, check yours. Alright. We have one more question to do after the announcement, but I have one more donut to give away.
They are $50 now until Tuesday, October 31st. Price will rise afterwards.
I
Buy
trust,
yours
I
now
trust.
to get a spot at the end
No,
of
I
your
don't
stay.
fucking trust.
Go to www.airbooksordercenter.com. Order number is 21027.
Diane!
Attention, students attending homecoming. A few reminders. Homecoming begins at 7 p.m. and ends at 11 p.m. The address is Hilton Miami Dayland Hotel. 9100 North Kendall Drive. The entrance to the ballroom is in the back part of the hotel with a drop-off loop for free parking for those driving. We're very welcome. Please remember, you are on the free parking day.
I have to, I'm about to pass out.
Students
just
who
me, I'm
take the
so tired.
exam
From
by
Brooklyn.
you, make sure that you are
I
here
cannot.
at
I'm
7:45
so sorry.
tomorrow. We
I will
will
not
send
be
you at 8 a.m.
I am going
You
to
do not
bed.
have to come in uniform, however, you should be
What?
appropriate.
I graded your exams the same day.
Students, we have about 16
I worked
detentions
till
this
10
afternoon.
p.m. that night.
16. How do you say 16 in Spanish, Emily?
Too many.
16. That is a lot. If you do not attend your detention that you scheduled with me, it is double
Multiply this by
next
how
week.
you have to change KPA to Pascal.
And this consider after announcements.
All right, so before we go, I just need to go over one more question. One more. Here we are. You're welcome for the donuts, by the way. Last question. It is paper one. I know it's your favorite. But what does it say? It's asking for the math, so that means I'm gonna want to use MR equals GRT over PV. But what do I need to solve for? G. So that means multiply both sides by? Right.
The one time you called me, I'm so glad. I literally, yes.
So let's first make the right formula. PV MR RT equals G. So that's our formula. Now what? Is the pressure in the right units?
Do we need to remember?
No, it's
340, no,
Or is it just the Pascal?
what's the number for
KPH.
It's 103,000.
273?
That's kilo.
It's 103,000, right?
8.41.
Volume. What's the right unit?
Meter.
Is that in meters?
Yes.
So times 5.37 times 10 to the negative 3. Multiply that by the MR. This is why I need your attention for this question. What's the molar mass?
It's a number.
No, ammonia, so it's NO3.
N close. NH3.
And
They gave you what it is, which means you have the
What?
molar mass.
NO3 is negative.
17.
Oh, it's nitrate.
Divide by 8.31. What's the temperature? What do we change it to?
137.
No,
333.
333.
And the final answer you should get is, if you worked it out,
I was
it's 3.4.
so close. I put Z when I put Z. I meant.
Oh, okay.
That's right.
Anyways, I just want to show you what it looks like in a Cambridge question. The only trick here is knowing that ammonia is NH3.
Yo.
Here's the homework. Remember, due when? Wednesday. Why? Just in case you need help during tutoring. All right. Have a wonderful weekend. I will not be able to. Yes, I will take a render.
That's online, right?
It is online. You did beautiful work on the last online homework I graded. Just it seems like a hassle.
It's time consuming.
It seems like a hassle. Make sure you get the homework before you leave.
I'm gonna be the first person ever.
It did
I
actually.
don't even use your call next
That is so
Today was
good.
my kind of class. Next class, your kind of class.
You got it right. Good job.
I think you have to do it.
I got it.
Can I ever?
Oh, wait.
Say what?
I feel like those are like they only have like 3 minutes.
What do you got? Grade related questions, I'm assuming? What am I assuming Oh, because of food. Oh, so you like that part?
Yeah, but it's also memorized.
To know the formulas. They make you know the formulas. Yeah, but you don't have to memorize it. They give you a formula sheet. It has 8.31 on it. You just have